This video is about two-factor analysis of variance without repeated measures. We discuss what you need two-factor analysis of variance for and what the difference is between one-factor and two-factor. Then we'll go over the hypotheses and the assumptions. After that, I will show you how to calculate the two-factor analysis of variance online with DATAtab, how to interpret the results, and we will also discuss what the interaction effects are. Finally, we'll go over the formulas so you can better understand what happens in two-factor analysis of variance. Let's get started. If we look at the most common types of analysis of variance, we distinguish between the one-factor and the two-factor analysis of variance, and on the other hand, the analysis of variance without repeated measures and with repeated measures. This video is about the two-factor analysis of variance without measurement repetition. This brings us to the first question: what do I need the two-factorial analysis of variance for? The two-factor analysis of variance tests whether there is a difference between more than two independent samples divided between two variables or factors. But what is the difference to the normal one-factor analysis of variance? Or what is the difference between single factorial and two-factorial? Let's start with the question of what a factor actually is. A factor is, for example, the gender of a person with the characteristics male and female, or the form of therapy used for a disease with therapy A, B, and C. Or it could be the field of study with, for example, medicine, business administration, psychology, and math. In the case of analysis of variance, a factor is therefore a categorical variable. You use an analysis of variance whenever you want to test whether these categories have an influence on the so-called dependent variable. For example, you could test whether gender has an influence on salary, whether the therapy has an influence on the blood pressure, or whether the field of study has an influence on the duration of study. Salary, blood pressure, and study duration are then the dependent variables. In all these cases, you can now check whether the factor has an influence on the dependent variable. Since you only have one factor in these cases, you could use a single factor analysis of variance. You're right if you say, well, in the first case we have a variable with only two categories, so of course we could use the t-test for independent samples as well. Now, of course, you may say, but I have another categorical variable that may also have an effect on the dependent variable, and I want to include that variable as well. Maybe you would also like to know if, in addition to gender, the highest level of education has an impact on salary. Or in addition to the form of therapy, maybe you would also like to include gender. Or in the third case, you would also like to know whether, in addition to the field of study, the university attended also has an influence on the length of study. Now, in these cases, you would not have one factor, but two factors in each case. And since you now have two factors, you use the two-factor analysis of variance. With the help of the two-factor analysis of variance, you can now answer three things. Once, whether the first factor has an influence on the dependent variable. Once, whether the second factor has an influence on a dependent variable. And then you can also make a statement whether there is a so-called interaction effect between the two factors. Therefore, in the case of single factor analysis of variance, we have one factor from which we create the groups. In the case of the two-factor analysis of variance, the group results from the combination of the expression of the two factors. If we have a factor or variable with three expressions and one with two expressions, we get a total of 6 groups that we want to compare. Now we have a good transition to the hypotheses. As already mentioned, you can test 3 statements with the two-factorial analysis of variance. So there are also 3 null hypotheses and therefore also 3 alternative hypotheses. The first null hypothesis is there are no significant differences between the groups of the first factor. Then, of course, there is the second one. There are no significant differences between the groups of the second factor. And the third null hypothesis reflects the interaction effect. One factor has no influence on the effect of the other factor. What this interaction effect exactly means will be discussed later in this video. And in addition, there is the alternative hypothesis, which says in each case that the factors have a significant influence, and in the case of the interaction effect, at least one factor has an influence on the effect of the other factor. And with that, we can now come to the assumptions. Let's first look at the scale level. The scale level of the dependent variable should be metric. That of the independent variable, the factors, should be nominal scale. So the dependent variable could be, for example, salary, blood pressure, and the study duration. These are all metric variables. And the independent variable should be nominally or ordinally scaled. For example, gender, high school degree, or type of a therapy. Note, however, that rank order is not used for ordinal variables, so this information is lost. Let's move on to the next assumption. The next assumption is about independence. The measurements should be independent, meaning that the measurement from one group should not be influenced by the measurement from another group. If this was the case, we would need an analysis of variance with repeated measurements. The next topic is homogeneity. The variances in each group should be approximately equal. This can be checked with the Levene's test. And finally, the last requirement, which is about the normal distribution. The data within the groups should be normally distributed. With this, I will now show you with an example how to calculate the analysis of variance online with DATAtab. Then we will discuss how to interpret the results, and we will also talk about what the interaction effects are exactly. And finally, we will come to the formulas. Let's take a quick look at an example. Let's say you work in the marketing department of a bank and you want to find out whether gender and whether one has studied or not has an influence on the retirement planning. So your 2 independent variables, or the 2 factors, are gender and whether one has studied or not. Your dependent variable is attitude towards retirement planning, where 1 means it's not important to me and 10 means it is very important to me. After all, is attitude toward retirement planning really a metric variable? Let's just assume that attitude toward retirement planning was measured using a Likert scale, and thus we consider the resulting variable to be metric. This example consists of only 20 cases, which is of course not a lot, so we have a very low test power, but as an example it should be fine. To calculate a two-factor analysis of variance online, simply visit datatab.net and copy your own data into this table. Then you click on Hypotheses test. Under this tab, you will find a lot of hypothesis tests, and depending on which variable you click on, you will get an appropriate hypothesis test suggested. If you copy your data up here, the variables will appear down there. If the correct scale level is not automatically detected, you can simply change it under Variables view. We want to know if gender and whether you have studied or not has an influence on your attitude towards retirement planning. So let's just click on all 3 variables. DATAtab now automatically gives us a two-factor analysis of variance without repeated measures. We can read the 3 null and the 3 alternative hypotheses here. Afterwards, we get the descriptive statistics and the Levene test of the variance equality. With the Levene test, you can check if the variances within the groups are equal. The p-value is greater than 0.05, so we assume equality of variance in the groups for this data. And here we see the results of the analysis of variance. We'll look at these in more detail in a moment. But if you want to know exactly how to interpret the results, you can also just click on the summary in words. In addition, you can check here if the assumptions for the analysis of variance are met at all. But now back to the results. Most important in this table are these 3 rows. With these 3 rows, you can test whether the 3 null hypotheses we formulated earlier are retained or rejected. The first row tests the null hypothesis, whether being a student or not, has an effect on the attitude towards retirement planning. The second row tests whether gender has an effect on the attitude, and the third row tests the interaction between being a student and gender. You can read the p-value in each case right here. Let's assume we set the significance level at 5%. If our calculated p-value is less than 0.05, then the null hypothesis is rejected, and if the calculated p-value is greater than 0.05, then the null hypothesis is retained. Thus, we see here that all 3 p-values are greater than 0.05, and therefore we cannot reject any of the 3 null hypotheses. Therefore, neither whether one has studied or not, nor gender has a significant effect on the attitude towards retirement planning. And there is also no significant interaction between having studied and gender with respect to the attitude towards retirement planning. But what exactly does interaction mean now? We will now go through this in more detail. To do this, let's first take a look at this diagram. The dependent variable is plotted on the y-axis, in our example the attitude towards retirement planning. On the x-axis, one of the 2 factors is plotted. Let's just take gender. The other factor is represented by lines with different colors. Green is studied and red is not studied. The endpoints of the lines are respectively the mean values of the groups. So this point is the mean of male and not studied. This point is the mean of male and studied, and the same on the other side for female. Therefore, here you can see that the male and studied group has a higher mean than the male and not studied group. However, you can also see that the group of females each have a higher mean than the group of males. In this chart, one can see that both gender and the variable of whether one has studied or not have an impact on the attitude towards retirement planning. Women have a higher value than men, and those who have studied have a higher value than those who have not studied. However, it can be seen that there is no interaction between the 2 factors. The influence of gender on the attitude towards retirement planning is independent of the variable whether one has studied or not. And the other way around, the influence of the study status on the attitude towards retirement planning is independent of gender. No matter if male or female, there's always the same difference between studied and not studied. So whenever these lines are parallel to one another, there is no interaction effect. Let's look at 2 more cases where there is no interaction effect. In this case, gender has no influence on the attitude towards retirement planning, and only study status has an influence, and there is also no interaction effect. In the next case again, whether one has studied or not has no influence, only gender has an influence. But now finally to the interaction effects. For that we compare these two diagrams. In the first case, we said there is no interaction effect. If a person has studied, he or she has a value that is, say, 1.5 higher than a person who has not studied. This increase of 1.5 is independent of whether the person is male or female. We have a different situation in this case. Here, studied people also have a higher value, but how much higher the value is depends on whether one is male or female. If I'm male, there is a difference of, let's say, 0.5, and if I'm female, there's a difference of 3.5. So in this case, we clearly have an interaction between gender and study because the two variables influence each other. It makes a difference how strong the influence of studying is depending on whether I'm male or female. In this case, we have an interaction effect, but the direction still remains the same. So women have higher values than men, and studied people have higher values than people who did not study. Of course, one could also get the following results. In this case, studying would have no influence at all on men, but only on women. So the mean value is exactly the same for men, regardless of whether these people have studied or not. Or let's look at an even more extreme case. In this case, men would have a higher value for those who have not studied, and women would have a higher value for those who have studied. So now let's go into the formulas needed to calculate an analysis of variance. What does the analysis of variance actually do? Or why is the word variance actually in the analysis of variance? In analysis of variance, the total variance of the dependent variable is divided into the variance of factor A and B and the variance of the interaction and the error variance. What does that mean? The independent variable under consideration has some variance. In our example, not every person will have the same attitude towards retirement planning. Some people will regard it as more important and others will say, well, that's less important to me. We now want to know if this variable depends on the variables gender and study status. So we want to know if we can explain some of the variance by the variable gender, study status, and also by their interaction. The portion that we cannot explain by these three aspects then accumulate in the error. SS stands for sum of squares. If the result would look like this, for example, we would be able to explain almost the entire variance through factors A and B and their interaction, and we would only have a very small proportion that could not be explained. This would mean that we can make a very good statement about the attitude towards retirement planning purely through the variable gender and study status and their interaction. In this case, it would be the other way around. Here, gender, study status, and the interaction has no influence at all on the attitude towards retirement planning, and everything accumulates in the error. Perhaps age has an influence or place of residence or quite a few other variables, but we don't know that. It all accumulates in the error. Now comes the big question. How do we calculate the different sums of squares? We will now go through this using our example. Here we have our data once not studied, and once male and female. First, we calculate the mean values we need. We calculate the mean value of the individual groups, thus of male and not studied, that is 5.8, then of male and studied, which is 5.4, and we do the same now for female. Then we calculate the mean value of all men and women and the mean value of non-students and students. Finally, we need the total mean value. With this, we can now start and calculate the required sums of squares. Let's start with the total sum of squares. For this, we calculate each individual value minus the total mean, square this, and sum up all values. The total mean is 5.4, so we calculate 6 minus 5.4 squared plus 4 minus 5.4 squared to finally 3 minus 5.4 squared. Together with the sum of squares and the degrees of freedom, we can then calculate the total variance. The degrees of freedom here are given by n times p times q minus 1. N is the number of people in a group, which is 5 in our case. And P and Q are the number of categories in each factor. We have in both cases two groups, male and female, or not studied and studied. With that, P and Q in our case is 2. Thus, we receive for the degrees of freedom 19. The total variance results with the square sum divided by the number of degrees of freedom. So we get 4.46. Now we can calculate the sum of squares between. For this, we calculate the group mean minus the total mean. So 5.8 minus 5.4 squared plus 5.4 minus 5.4 squared, and the same for these two values. In this case, the degrees of freedom are 3, which gives us a variance of 2.53. Now we can calculate the sum of squares of factor a and b. We do that with this formula. A dash is the mean value of the categories of factor a. So we calculate 5.9 minus the total mean value and 4.9 minus the total mean value. Together with the degrees of freedom, we can now calculate the variance for factor a. We do the same for factor b. In this case, we use the mean values of male and female, and we get a variance of 0.8. Now we can calculate the sum of squares for the interaction. We obtain this by calculating the sum of squares between minus the sum of squares of a minus the sum of squares of b. For the interaction, we get a variance of 1.8. Now we have almost done it. Finally, we can calculate the sum of squares for the error. This is calculated similar to the total sum of squares. So again, we use each individual value. Only in this case, we do not subtract the total mean from each value, but we subtract the respective group mean from each value. So in this group, we subtract 5.8 from each individual value. In that group, we subtract 5.4. Here we subtract 6, and then we subtract 4.4. So we get 6 minus 5.8 squared plus 4 minus 5.4 squared to finally 3 minus 4.4 squared. This gives us a sum of squares of 77.2 and a variance of 4.83. And now we can calculate the f values. These are obtained by dividing the variance of factor a, b, or the interaction by the error variance. So we get the f value for factor a by dividing the variance of a by the error variance, which equals 1.04. We can now do exactly the same for FB and FAB. To verify, we get exactly the same values with DATAtab 1.04, 0.17 and 0.37. For the calculation of the p-value, you need the degrees of freedom and the f distribution. So with these three values, you can either read the critical p-value in a table, or as usual, you just use a software to calculate the p-values. I hope you enjoyed the video and see you next time.